Okay, welcome everyone to Implementing Binary Protocols with Elixir. We are 15 minutes late, so I better go quick. Just kidding. We'll just run over time then. Well, if you read through this topic, Implementing Binary Protocols with Elixir, the first thing this could come to your mind, because when we had the question in the other room, like who of you still do Java, I basically saw all hands up. So let's stop for a second. What is Elixir? Who of you know what Elixir is before I start explaining it? Okay, keep your hands up if you have written some Elixir. Okay, keep your hands up if you have Elixir in production. Okay, that's just me. Oh, over there? Awesome, awesome. Okay, so that makes 3 of us. I appreciate you having written something. And for the rest of you, Elixir is a Ruby-inspired language running on the Erlang virtual machine. Thus, it follows the Erlang concurrency model, which might be a little bit familiar. So it uses actors as concurrency model. That might be familiar to you from akka. It's a functional language, and in order to make the concurrency model work, all data in there is immutable. In this talk, it's basically introduction to Elixir, like guided on a topic of implementing a binary protocol. If you see a language construct that doesn't make any sense to you, please feel free to ask, but I'm the timekeeper here, and if I feel this is like going to take way too long, I will just tell you that. If we have time at the end, we'll go over that, but if there's something unclear, I try to explain it really quick. But there are some concepts that usually, you could fill up a whole talk just with a single concept, so it's hard to explain it in 1 minute. Let's talk about the motivation for this talk. I'm a web developer. Since I started programming, I did software for the web and web applications. And if you're also a web developer, there's one known fact we all share and we all know, and that is that the web is screwed, right? It's totally outgrown its original intent. When Sir Tim Berners-Lee had the idea of what the web could be like, it was like non-styled documents that were interlinked to each other. And then he even had the idea that the browser could be something like an editor. We are totally away from that, and what we now have is this like Tinder. So, and it's still the same protocol, so you see the web is really screwed. It's completely outgrown its original intent, as I mentioned, and thus it's really slow, because it just was not made for what we're doing with it at the moment. You know, you're really riding the horse on the wrong way. So 3 years ago, and that was the only stats that I could gather, the average website had 101 assets altogether, were 2.6 megabytes big, spread over 38 different TCP connections. Each TCP connection with its own handshake, and most often, even worse, with its own SSL handshake on top of that. So there's a lot of round trip. But HTTP2 is here to the rescue. The IEFT, the Internet Engineering Task Force, was aware of this issue for a long time, and they came up with the idea to fix it. Well, it's a community-run effort, the IEFT, so it was not the IEFT. Like they were, oh yeah, we really want to fix it, but we don't know how, and then they couldn't agree. So Google went ahead and implemented Speedy, which then became the base of HTTP2. But today they're completely unrelated. It's just that they're very similar. But so let's take a quick look at HTTP2, because this is basically the problem domain we are looking at in a second. First of all, you need to know that it's compatible, so it's not going to break the web. Headers will stay, methods will stay, and the concept of request-response cycles is also still there. And also, as I mentioned, it's not breaking the web, so you will never see like HTTP2:// somewhere on the web. So that all of that will stay, because we already figured that with encrypted connections, we basically broke all links out there, right? So whenever you link to an HTTP something document, and if it's now only available in HTTPS, like the link changed, and the idea of interconnected documents kind of broke. It's also multiplexed, and this is how we fix the speed issue. Multiplexing means that it uses streams in order to transfer multiple resources on a single connection at the same time. And this is something that was not possible in HTTP1, and we did like all kind of crazy hacks in order to work around it. Most often, we spreaded documents on assets over multiple TCP connections, thus giving us the issue that we had so many TCP handshakes and round trips. How does it work? We have a physical TCP connection, the HTTP2 connection. Each consists of logical streams, and on the streams you will have the frames. So the streams are just a logical concept, while you have the physical TCP connection, physical, and then binary frames transferring on this connection. But each frame contains or belongs to a single stream, so that way you can group them together, and each stream usually is a request-response cycle. And Frames don't have to be in order, they can be in any order, and thus now with HTTP2, the only limitation we have is the bandwidth. So there's no ping and no round trip involved anymore for multiple assets. Let's take a look at the frames, because the frames are the interesting part, and this is where we come to the meat part of the talk. The frames are binary. And this is probably also the biggest difference to HTTP1. It's not a text-based protocol anymore, it's a binary protocol. And whenever we talk about binary protocols, this is something you see more often. That's a so-called frame layout, and it always describes like how this never-ending stream of bits actually fit into something that makes sense. So in a struct, right? Because on the wire, it's just a never-ending stream of zeros and ones, and we have to make sense of it. Like our application has to make sense of it, especially because it's not a text-based protocol where you could just chop at the end of the line, and then you have a line that you can parse. So this is not the case anymore. But this was also what it makes so efficient. So we start here with a length, and the length is 24 bits. Then we have 1 byte type. We have 1 byte flags. Don't worry. Have a seat. I appreciate you coming to the first line. Usually no one sits there. Then we have the reserved bit. That's really weird. It's always 1. Don't ask. If you want to hear the whole story, just come up later. And then we have the stream identifier, which is 31 bit. And then there's the frame payload, and this is basically its own frame layout again, or its own kind of type. So whenever we check out the different frame types, keep in mind that this header is always on top of it, and what we're looking now is just this part. So there are 10 different frame types, like data, like settings, reset, there are arrow cases, frames, all different kind of stuff, but we want to take a look at the header frame. Header frame is usually what initializes a request-response cycle. So it's initial package, and also it represents the HTTP headers, because we mentioned that will stay, all of this concept will stay, so we have to have a concept of headers in here. This is how it looks like. It has the pet length at the top. It's an exclusive bit. It's a stream dependency. You can have dependent streams in order to manage content. There's a weight. This kind of belongs together. And then there's a header block fragment and a padding. The padding you see over here is a security feature. It's for a text. It's implemented against a text called breach and crime. If you're a security kind of person, you really want to check this out. It's kind of interesting. But I think security topics are that important that I don't want to go into more detail on this because I probably can't get it right out. I just want you to know that it is a security feature. This is the header block fragment, and this is also what we want to take a look at. This is how it would look like implemented. So we had a pad length of 0, then we have an exclusive stream dependency of 0, then there's a stream dependency. It has a weight of 16, and then there's the header block fragment and the non-existing padding. So padding is 0, so we don't have this padding in here. And today, I'd like to take a look together with you at this block. This is the header block fragment, and the header block fragment is HPACK encoded. This brings us to another feature of HTTP2, that is that headers are now compressed, right? This is also something new, and you will see in a second why this is probably one of the most amazing features of HTTP2. I mentioned the encoding protocol on how this is encoding is called HPACK. So let's take a look at HPACK. HPACK is defined in RFC 7541. And it's a different spec than HTTP2 is. And basically, it's decoupled for the same reasons. You're decoupling software. You can update it without the big dependency, and you have a smaller scope to reason about. So you could possibly implement HPACK and use HPACK out of a different context than HTTP2, but it probably doesn't make sense. So this also might raise another question with you, like, why would anyone implement this on their free time? Because this is basically what I did. I implemented HPACK because I thought it was fun. Turned out it is fun, and I had the idea to write a web server in Elixir. That is not fun, but it was an interesting, or still is an interesting exercise. And that is kind of the motivation why I wrote HPACK. So let's take a look at how HPACK works and compresses headers. On the left side here, you see the different headers you have. So you have method get, scheme, HTTPS, hostdn, simple.com, and so on and so forth. And HPACK then uses a table, the header compression table, in order to compress this. The table consists of a static part and a dynamic part. The static part is specified in the RFC and usually should never change. And then there's the dynamic part, which has ongoing indexing, but is built up over the connection. And then this is how you encode it. So if you have a matching key-value pair like method get, you can just encode it with transferring a single integer. If you have scheme HTTPS, this is something you see over the web like all over, right? Imagine how many bytes we waste in transferring on a text-based protocol these two headers, right? We send this back and forth all the time. On every request we make, we send this, and there's no point in there. So we can also represent this with a single digit. And the host, for example, on a single connection, the host usually doesn't change. So you can add this to this dynamic table. And here's also a thing that really stands out in HPACK is that the header compression table is stateful. So even though HTTP is completely designed to be a stateless protocol, in HTTP2, this is the only part that contains state. So in between requests, the header compression table contains state in order to maintain this dynamic table. But the whole request response cycle is still and should be still stateless, and also this is bound to the connection. So once the connection drops, you will start off with a fresh dynamic table. So let's take a look at the format of this, like how are the integers actually encoded. The first thing you want to encode is the digit 2, right? So we know it's method get. And this is how it looks like. It's always like byte bounded, so we start at 0, goes up to 7, and when we see that the first bit is set, we know that this next bit will actually be the index that is encoded. So when we're going through these different header fields, I really want you to take a look at the beginning, because this is where the interesting stuff happens. So here we have a literal header field with incremental indexing, which basically means whatever header is transferred, you should add this to the table. So here, the first bit is 0, second bit is 1, then we have the index, which means the header value, the header key, and then this is always a string. So whenever you see this concept, like age indicators and the Huffman indicator, value length and value string, this is always a string. So that's a basic string representation. And if it's the header key and the header value not known, you would basically transfer both. And here again, if I see that the first bit is 0, next is 1, and then there's an index, or if it's 0, 1, 0, I exactly know how to parse the rest of the binary stream, right? Same for literal index field without indexing. This means that it should not be added to a table. And then there's also never indexed, which is for intermediaries like proxies and stuff. And here's the same thing. Just telling by the first bits here, you can tell what logic you have to apply in order to parse that. And we'll make use of that in a second. So let's have a look on how we can implement HPACK and Elixir. Before we can do this, there is a little bit of Elixir knowledge we need. And this is why I want to take this digression really quickly. And the first thing we should learn about is pattern matching. So let's fire up a console and start IEX. IEX is the interactive Elixir shell. It's basically a REPL, like Pry and Ruby or Node, or there are tons of these kind of stuff. So I can basically type code. It will evaluate and print out the result. First thing I do is x equals 1. This looks like totally normal to you, and I think you all know that the value of x is 1, right? This just makes sense. Well, what happens if I do 1 equals x? It already kind of gets weird, right? Because usually in languages, this assignment cannot work because you cannot assign something to primitive type. And I think I can reveal what's going on here if I show you that 2 equals x actually gives you a match error. Because what you see here in line number 1 is not an assignment as you know it. It's called a binding. So we bind values because the equal is not an assignment, it's a pattern match. So we always match the right-hand side to the left-hand side. And if the left-hand side is not bounded at the moment, so it's an unbound variable, we'll just bind the value that it is on the right-hand side to the variable. So here, we bind the value 1 to x. And this is why this also makes sense, because it's a pattern match, and we match that the 1 is 1, and it just returns the matched value, which is 1. And this is also why line 4, 2 equals 1, is a match error, because the right-hand side doesn't match the left-hand side. This is basic pattern matching. You can do this with more complex structs, like a tuple. A, B, C are all unbound here, so the pattern match gives you hello, world, and then 42. A is Atom called hello, then there's the string world. and C would be 42. Just believe me here. And if we do the same pattern match, again, with a not complete struct, so it's 3 values on the left and only 2 on the right, again, we get a match error. So we can also match on more complex types. This is a pattern you will see more often in actual Elixir code, because imagine this is not a single tuple, but rather a more complex function call deep into your system. And with that match, you always can be assured that it was okay. So whatever happened in there was okay, and if it was not okay, like this is an error atom, the code will blow up. Code blowing up in Elixir is not a bad thing. There's this concept of let it crash. And this basically means that you should let your code crash in an exceptional case, and then just let the VM handle the restarting with supervisors. That's a really interesting topic. If you want to learn Elixir, I really recommend to take a deeper look into that. Now, let's take a look at how we would encode something, right? We want to encode a value. Yeah, we want to decode, sorry. We want to decode the header block fragment. Sorry, there's more Elixir we need to take a look at. And that's the second bit, and I promise that's the last bit where we take this digression, and that's basically strings and binaries. In Elixir, that's the same. Strings are binaries. A string in Elixir is a UTF-8 encoded binary. And what's even more funny is that there is no native type string. Whenever you see the type string in Elixir, it's a custom type. It's a custom type that the engine ships, but it's not like int or binary native type, but it's rather a made-up type. I can show you an example in IEX again. So let's fire up IEX. And then there's the question mark helper, which always gives you the UTF-8 code point of a character. So E is 101. And this double bracket syntax is the syntax you use to create a binary. Here we also have the modifier UTF-8, but you can also leave this away because this is only used for pattern matching. So this way we can construct a binary, and if the binary only contains printable code points, the console is responsible for printing it out as an actual string, right? So the whole data within the VM is all binaries, and only the presentation layer is responsible to convert it into something that you could read. Let's take a look at another example. So we have the string Jose bound to the variable string. It's a pattern match, and here's another trick. If you append a non-printable character, like a 0, it's always non-printable, you will see that it will point out all the different code points. Leaving the 0 out, there's something weird, right? It's 5 code points for a 4-character string. And that is because the E is not a regular E, it has the E with X on. You can do this with emojis and bangs and longer strings. And now let's take a look at Elixir code. So what we do here is we define a module because it's a function language. There are no classes. It's just modules that holds up functions. It's basically namespacing. And here the first thing we do is we define our custom type. It's a custom type header. We're dealing with a lot of headers, so having this type makes a lot of sense. And the header is always a tuple of 2 strings. And here you see that it's not a native type, because a native type looks like this. And this is a custom type. That's the type spec. Type spec in Elixir is usually, a type spec combines both worlds, like a dynamic type and a static type language, because Elixir is a dynamic type language, but with type specs, you can have compiler warnings if something does not make sense if you have type specs. But these are completely optional, and you can leave them away if you think it is good to do that. So what do we have here? We have the decode function. Decode function takes a string, which is like not 100% correct because it should be a binary, but a string is a binary, so they're like equal. But it would be more precise to tell that this is a binary. And it takes the PID. A PID is again a custom type. It is a process ID, and a process is usually what you know as an object instance, so it holds state. And that is the compression table. Like it is basically the representation of a table containing the static part and the dynamic part. So what do we do here? Well, we call another function called parse and add the result list. So when we pass a header, we prepend it to the result list. Again, these are the headers you want to encode, and this is the header block fragment we want to take a look at. So let's take a look at the first byte here. It starts with a 1, so we know that this is an indexed header. So we know that this must be an integer that just represents a single key value pair. So in code, it looks like this, right? So we have the private function parse, and it gets a binary. So here you see the binary constructing pattern, and then it also gets the header list, which is at the moment just an empty list, and the table. I think getting this line in makes it a little bit, might help a bit. And if you take away anything from this talk, I want it to be this slide. Because in this slide, you see everything what makes Elixir great in order to implement binary parsing and binary pattern matching. Because we do a couple of things here. First, it's a pattern match in the function header. So we can deconstruct the binary we get in the function header. Right? There's no custom code needed. We can just pattern match that the binary we get passed in is a 1 at the very beginning. So that is that. Right? It has a size of 1 because it's just 1 bit. And if that's size 1, we know this matches. And then we bind rest in here to the rest of all of this and the remaining bytes are in this variable. And then there's the empty list and the table, which is the pit. First thing we do is we parse out the integer. Here we see it's a 2. Then we ask our table for a lookup, so we know it's method get. And then we call parse again. And this is the next thing that I think is pretty amazing, because we pass in the rest, and then here we have this yet empty list, which is the tail, and this is the head. So we construct a new list because everything is immutable. And that is a single header, so that is the head of the list, and this is the tail, so we construct a new list of result headers. And we will see how this looks in a second. So this is a recursive function, because in Elixir, it's a function language, there's it's immutable, so there are no loops. So we call parse again, and I spare you the details because it's again the same index, so we do the same stuff. I just want to point out that we now have one header in the list here. First thing we do is we parse out the integer, then we look up the header. Now we know it's scheme HTTP, and then we do, again, same thing, we append it. We call the same thing again. We know it's, again, a 1 at the beginning, so we do the same thing. We parse out the int, we look up the table, we know it's parse slash, and then we call parse again. Now it gets interesting, because you can see over here that this does not start with a 1, right? So when we call parse, it is not this function that matches. And this is another amazing thing in Elixir, because you can have the same function definition with the same name and the same number of arguments, so the same arity, but having a different body. So we can define the same function all over, and the compiler, the runtime, will try to execute every function from the most top one to the most low one, and will execute the first one that matches. And this is why a pattern match in the function header makes so much sense. So here, we match that the first bit is a 0 and the second bit is 1. And this is just a shorthand, like colon number is a shorthand for the size modifier. So we don't have to call like size all the time. And then if we have this header, we know that this is going to be a literal header field with incremental indexing and an index name. And we can have all this information and all this binary parsing in the function header. I think that's pretty amazing. So let's take a look on what we do here. We pass an integer out of the, so we pass out the index, then we pass the string, so to have the value, and again, we just parse like the whole thing because it always looks the same, so we have this helper function here. We will see this in a second as well. And then we look up the header because we want to add the key and value pair, so we have to look it up from the table, and then we add it to the table. Here you see we pass the pit, and the pit, again, holds the state. So we basically modify the state that is kept in this process. And then we call parse again. Here it's going to be interesting. Because it's a recursive function, we need a kind of a termination function, right? We cannot have it going on forever. We need a state, a defined state, where we know that we're done parsing. And this is, again, a pattern match, because this matches an empty binary. So it's a binary, but it's not, there's nothing in there anymore. And then we match the headers, and then whatever we get past here, we just ignore it. And then remember, we always prepended it to the list, because this is way faster, because a list in Elixir is a linked list. So prepending is really fast. And the protocol defines that headers should not change order, so we need to reverse it at the end in order to have the order maintained. So we have method get, scheme HTTP, parse slash, and authority www.example.com. Now, let's take a look at the header block fragment again. The first byte was method get. next byte was scheme HTTP, next byte pass slash, next byte was just the authority key, and then all of the rest, all of this was www.example.com. And I think this really shows why header compression makes a whole lot of sense in order to have less transfer rate on the wire and save a lot of time, especially on low bandwidth connections. Because all the headers that are known to each client or server, you can just represent them in basically 1 byte or a bit more if it's a longer index. But you can represent in a really short way, and I think that's impressive. So let's take a quick look on how strings are decoded. It's again a pattern match here, because this indicates if the string is Huffman encoded or not. If it's not set, we know that the string is not Huffman encoded. Then we take a look at the integer, so we know the length we have to parse. And this is again a pattern match, but like a binary deconstructing pattern match, but you can also do it in line, right? There's no need to only do it in the function head. You can do a pattern match wherever you want. So what we do here, we pass out the value, we tell the VM that it's a binary and has the size of length. And what you also could do, but due to the weird implementation of the protocol, it's not possible in HPACK, you can have this size, like this value of length, parsed out here. So if you have a binary where the first bit is the length, and then the next bit is the actual thing you want to parse out, you can parse out a variable length out of this pattern match. There are tons of examples on how to parse MP3 and this kind of stuff, where the integer here is not variable, because here you see it's a 7+. So it says it's not always 7 bits. It could be more, because if the number exceeds what you can fit into 7 bits, this is not going to work, and this is why we need this extra step of parsing it here. And then we return the tuple of the value and the rest. Again, we always have to pass down the rest, because it's a immutable language, and this function basically cuts off or always generates a new version of the rest, so we have to pass it all the way through. This, I don't know if you notice the difference, is the Huffman encoded version, so it matches on the state that the bit here is set, and then it calls Huffman decode in the value. The rest is the whole same thing. If you know Huffman, Huffman is an encoding, it's a string encoding that encodes characters that occur most often with as little space as possible. And this is why in this implementation, all strings are usually Huffman encoded, because in the worst case scenario, it's the same length, and you would just waste a few CPU cycles in order to encode it. And the best case, if you have a string like that's 100 times A, you would save up to 88, 89, 99% of the space. So that's pretty cool. Now let's take a look at encoding. I could say, well, encoding is the same as decoding, but just the other way around. But we have a few minutes left, so let's walk through it all together. This is the public function, so it's encode. It gets the headers and the table. Here you see I left out the type specs, but in the actual implementations, it is there. And here you see another Elixir feature, and I think that's also pretty cool. It's called a guard. So it checks if the argument you pass is a list. And if this guard does not return true, this function header does not match. Right? That way, we can make sure that whatever we get in here is a list, and you can use the list functions. And you can have a different guard, so that way you can implement functions that take different kind of arguments and then transform it to a general state and use it further on without type hints, without like static typing. Just with this guard functions. And then this is another call to the encode function. This time we pass in the header list, again an empty binary and the table, which is the PID. And then we call encode, and this time we call encode with 3 arguments. And this is why, and I think this also was confusing to me in the first place, you can have the function encode defined twice, one private and one public. Because for the Elixir VM, these are totally different functions because the arity is different. The arity is the number of arguments. So this has 2 arguments, so it has arity of 2. This has 3 arguments, so it's an arity of 3. And for Elixir, it's completely different functions. And thus, I can have encode with an arity of 3 declared private, while encode with an arity of 2 is a public function. If this makes any sense. OK, let's take a look at what we do here. So again, this is a fairly complex pattern match we do here, but I think If you take a look at it, it's pretty great, because in every other language, you probably would waste like 2 or 3 lines just to get this working. So what we do here is we pass in the headers. We know it's a list of headers. So we again match the list and then get the first element out of the list, so the head of the list, and then that's the tail, so that's remaining headers. And then we know it's a tuple of a key and a value, so it's the header key and the header value. And we can match it out here as well. So right at the beginning of the function, we have the key and the value available, even though they were like hidden in a complex data structure. So then we need to know how we can encode the header. Oh, that's interesting. There you see Windows Finder. Can we close that? Thank you. Okay, we need to know if the header, like how we can encode the header. So we call table find with the key, the value, and the table. If it's a full match, that means we know the key, we know the value, we can just encode an index header, so basically encode a single number. If it's just a key match, it usually does encode literal index, because we assume that we want to add all headers to the table. And then it could be a non-match, and again we call encode literal not index, because we assume we always want to add this header to the dynamic table. And then we append the partial we just encoded here to the header block fragment, and then call encode again until we hit the termination function, which would be an empty list. So let's take a look at encode index, and this implementation is so easy that you can use the Elixir version of a shorthand function declaration, because it's a single line, right? You can encode a binary in a single line of Elixir. I think that's amazing. So you construct a binary here. You set the first bit with a size of 1, first bit, to 1, and then you encode the integer in version 7, as a bit string. Now let's take a look at encode literal indexed. We do the lookup, we add it to the table because we want to have it in the dynamic part, and then we construct a binary again. We set the first bit according to the spec to 0, second to 1, we encode the integer, and then we encode a string, because again, the string always looks the same. How do we encode strings? Well, encoding strings works like that. So you pass in a string. Again, in this implementation, it's always Huffman encoded, because as I mentioned, like the worst case scenario is a few CPU cycles wasted versus the complexity of having like an option set, which is not existent at the moment, or having the same size. I think it makes sense to always do that, unless you have a special use case for not doing it. Then we want to know the byte size, because that is the length we have to encode in here. And then, again, we call it like that. So we set the first bit to 1 in order to indicate that the string over here is a Huffman encoded string. And then we encode this integer 7. For this talk, I leave out the fact on how you would encode integers, because integer encoding is fairly complex in HPACK. If you're interested in how this is done, check out the specs or find out the different slide deck of this talk on Slider.io. It's explained in there. Basically, it uses a lot of bit shifting, and I wanted to spare you the bit shifting part here. So if you've read the abstract carefully, there was one thing promised, and that is RFC-based tests. And what I did there, I think, is really a great use case of the Elixir ecosystem. And I really want to share this, because I think that's such a cool thing. So let's take a look at the specs here. First of all, it has specs. I think that's pretty awesome. It's a side project, it has specs. I want to point out that fact. And then what we do here is that we do some setup. So this is a regular X unit. X unit is the unit testing framework of Elixir. That's a setup block, so that is run before every spec. We construct this table. Again, it's a process, so we have to start it. It gets the initial length, allowed length. And then we have this struct here, which is required by X unit to use it and reuse it in specs. This is the RFC I implemented the HPACK protocol after. And what is really cool is that first it's on GitHub, so that's awesome. It's not in this really ugly RFC IEFT toolbox. It's on GitHub, so it has a nice README rendering. And also, and this is like way cooler than the fact that it's on GitHub, it contains a whole lot of examples, sophisticated examples on how the whole encoding and decoding process works. It's like an example where you have 3 request response cycles going on everywhere with the with the headers to encode, then with a hex dump. I think that was helping me pretty much. And then how the decoding process works, how the intermediate steps looks like, and also how the dynamic table looks like at the end. So having these examples, I felt pretty confident that whatever I did in my implementation, if I just transfer the examples into specs, that my implementation is fairly solid. And turned out there was only one case that was not covered, and that I fixed at the moment now, or that I fixed like a few months ago. So let's take a look at the actual implementation. So this is the test for the literal header field with indexing. This is just a lot of shorthands because it would not fit on the slide otherwise. In the actual implementation, it's really long words. And this is what I have here. So it's the header block fragment, again, in a binary format, and then here's the comment of what it was, the hex dump. Then we call HPACK decode, and then we assert that the header in there was the actual header given, and we assert that the table size is also what was in the examples. But recall, this is what it looks like in the spec, and this is what I made here. So in order to create this, I used a lot of matching in the editor, a lot of multi-line editing. It was really cumbersome and tedious to do this like for every example. I had to do it over and over again. And in the end, this is not that helpful and cool to look at as the hex dump of the specs. So what I really wanted to have is like this thing, but in there, right? This is what would be awesome. But downside is that what you see here is it's just not working. It's invalid syntax. So no matter how hard I want to have this, it's just not going to work. But here's the trick, and I want you really to watch closely these 2 characters here, because this works. And I think this is what it makes so great and so awesome. The implementation is fairly simple. This is just a custom function call. It's called a sigil. That's the way regex is, for example, implemented in Elixir as well. But let alone the fact that I can use this struct in my specs and just copy and paste it from the RFC was so amazing. And you can see the commit where I did this all over. And if you check out the diff, it really makes the code like a whole lot more readable. So this is the implementation of the sigil. This is how you implement custom sigils. And given by the space you have here for the code, I will show it in a second, you can bet how complex it is. And probably there's a lot of room to improve, but on the other hand, it's just a spec helper. So this is what we do here. We start split line by line, remove the comments, we split by space into 2-byte chunks, then we flatten and filter out some junk, and then we convert the hex into integers. Anyway, this works. You can pull down the code and check. And you say, well, it's a lot of code, is it fast? And let's put up a console and check if it's fast. So we run the specs, and you see, this is the smallest number they can display. It was probably even faster. So even though we ran this code for all specs, a lot of times, it's not a performance impact. Also, because mixed tests are always per default asynchronous and uses every CPU you have at hand. That's also pretty cool. All of this stuff I've shown you is, as mentioned, it's available on GitHub. So it's in my namespace, nesquick/Elixir HPACK. There are a few Elixir implementations that uses that. That's pretty cool. So every HTTP2, especially the clients, there are a few HTTP2 clients, Elixir clients, they use this HPACK implementation. This is also how we found the one weird bug. The bug was because the ordering of the function, the pattern matching I showed you, so there's a lot of parse functions, and the ordering was wrong. That was really hard to spot, so that might be a downside of that. Then there's also Lie, that's the web server that has only a logo at the moment. So if you want to talk about writing web servers, I'm in for that. And now it's time for some final thoughts. Like when I did this, it was more an exercise to learn Elixir. It was the first Elixir project I did, but it really contained all the good parts and also a few of the bads, but a lot of the good parts. If you have such a problem at hand, and it is also good for other kind of problems, but especially the binary stuff, working with binaries, deconstructing, protocol parsing, TCP, binary streams, all of this kind of stuff. Elixir, and when I say Elixir in this entire talk, it also means Erlang because it's the same VM, it's the same types you have. I don't make any use of just special Elixir features. It just works amazing. And if you have such a problem, I really can encourage you to take a closer look on this. We need a few seconds for advertisement. All of this was brought to you by DN Simple. That's the company I work for. I brought a whole lot of swag, so I have shirts, I have stickers. If you want that, come find me afterwards. But we're not a swag company, even though we have a lot of swag. We are a DNS-hosted domain automation provider, so we solve all problems you have with domains. We offer an API where you can register domains, set records, and we offer all kind of integrations with Terraform, Chef, Puppet, Ansible, whatever you want. If you want to give it a spin, you can use this code. You get a 3-month extra. You start with a 30-day trial, and then you get 30 days more, so you have 2 months of testing it. Or if you want to talk any more DNS, just come afterwards and find me. That is me. That is me without a beard and with short hair. It's really long ago, 2 years. My name is Ole Michaelis, as I mentioned at the beginning. If you have any feedback or you want to stay in touch, use that. That's probably the best way to reach me. That's my Twitter handle, CodeStars. If you're into following on GitHub, I don't know what you're doing, but you can do that here. And I have a blog where I don't blog. It's at codestars.eu. I think they now call it a website. It was intended to be a blog. And that is basically it. That's all I got. Thank you very much.